What we want to do now is we want to interpret the value that the standard deviation gives us. And so what we can do is if we graphically look at some data sets here, they all have a mean of 5. When the standard deviation is 0, all of the data is in one place. As the standard deviation grows, the data spreads out from the mean. In fact, it can spread out far enough with this standard deviation that there's more away from the mean than closer to it. Though that's not always the case. We'll tend to get a uniform shape from these. But the larger the standard deviation, the greater the spread. So if we look at data like this, here, this standard deviation has to be 0 because all 8 pieces of data are chunked within the first bar. Well, here, 4 pieces of data are 1 standard deviation negative, and 4 pieces of data are 1 standard deviation positive. In fact, the data is 1 standard deviation away. Here, we have 2 pieces of data that are a distance of 1 away, and we have 2 pieces of data that are a distance of 3 away. So on each side. So we're looking at like square root of, let's see, 4. We're looking somewhere between 2 or 3 if we were to estimate these. And so let's see, each 8 entries is 4. The deviation of each entry is 0 because everything's in the same place. So that was a good estimate we could do. Here, all 8 entries are 1 standard, are 1 away, and so the standard deviation is 1. Here, it's +1 or +3, and so it's somewhere between 1 or 3, so it's a 2 something. And if we calculated this data exactly, we would see it's 2.2. Now, standard deviations lead to this nice thing called the empirical rule. And the empirical rule is a way that we can figure out the percentage of data that lie within a standard deviation. So symmetric data follows the empirical rule. So the data has to be symmetric. And what this kind of means for us is, and I'll come over to the chart, is if the mean is representing our truth and things only deviate by random chance, then in the fall, it's more rare for things to fall further away. So we can count, things will stack up near the mean. And the standard deviation, because it's weighted by how the data is spread, will always kind of talk about the same boundaries. If the data is spread out further, the standard deviation itself is larger, but the amount of data is in the same place. So the empirical rule lets us work our way through percentages of the data. And so with 1 standard deviation on either side of the mean, there's 34 and 34, or 68% of the data. Looking at the distance from 2 standard deviations on either side of the mean, there's 95% of the data. And within 3 standard deviations on either side of the mean is 99.7% of the data. And this actually becomes an intuitive way that we understand statistics without ever having taken statistics. And we'll look at some data sets where we look at height, and generally things outside of 2 or 3 standard deviation, if you look at the average height of people, is what you would call tall. On the positive side, people outside of 2 and 3 standard deviations of height you would call short. And this is your brain processing all of the people you've ever seen and figuring out what's rare or not rare. And it can talk about where the bulk of a population lies. Let's use the empirical rule a little bit here and see how we can set these boundaries. So we're going to look at the sample of the mean height of women was 64.1 inches. and the sample standard deviation was 2.6 inches. So we want to estimate the percent of women whose heights are between 58.9 and 64.1 inches. Now, notice 64.1 is the mean, so we're looking for something less than the mean to the mean. I'm going to switch over to my blackboard here. So 64.1 is the sample mean, and the standard deviation is 2.6. And what we want to do is we want to estimate from 58.9 to 64.1. So what is the percentage between 58.9 and 64.1? I'll draw my Pac-Man ghost, or my Gaussian curve, or bell curve, or normal curve, and I'll label my mean here as 64.1. Now, since the values do not go above the mean, we're looking at things on this side of the standard deviation, or this side of the mean. And so we're looking for x bar minus 1 standard deviation and x bar minus 2 standard deviations. I have to make my s's a little more loopy so they don't look like 5s. And so that's 64.1 minus 2.6 and 64.1 minus 2 times 2.6. So 64.1 minus 2.6 is 61.5. And 64.1 minus 2 times 2.6 is 64.1 minus 5.2, which is equal to 58.9. So 2 standard deviations is the percentage we're looking for. So we're looking for the percentage of the data that's within this region. Well, if we go to our empirical curve, or a bell curve with our empirical rule on it, we can see that there's 34.13% and 13.59 exactly in between those two. Of course, we could estimate it as 34 and 13.5, right? And we're looking from here to 2 standard deviations. And so that's going to give us 57.5% using this chart. If we use a slightly more precise chart, it's 34.13 here and 13.59 here. And that's going to give us 47.72%. And I said 57 point on the other one. I meant 47. Sorry, bad adding in my head. And so 47.72% of women have height between 58.9 inches and 64.1 inches tall. What we want to note here is if you look in Chapter 2, Section 4 of the book, there's a slightly more accurate empirical rule, and it adds the smaller decimal places. So rule of thumb, it's 68%, but it's closer to 34.13 plus 34.13, which is 68.26. And so in Section 4 of Chapter 2 of the book, you get this much better value of the distribution. And I have found that Pearson, when they ask for empirical rule questions, will use these percentages on it. Again, the empirical rule is a rule of thumb for turning standard deviations into the amount of data. And we're later on in chapter or section 5 going to find a way of talking about these percentages a little bit better. And in Chapter 5, we'll explore the percentages in full detail. This is actually part of statistics that in most statistics at this level, we look things up on tables because finding these values come from integral calculus. And this actual function that makes the bell curve and some of the other distributions we look at are really hard to do integrals for. So what was nice is mathematicians a couple hundred years ago made tables of all the answers so that people could look them up instead of having to calculate them by hand. And we all have our technology to help us. Well, if our data isn't symmetric, then we'll get Chebyshev's theorem. And Chebyshev's theorem, instead of talking about percentages, we'll talk about fractions. But we can always turn a fraction into a percentage. And what this says is the portion of any data set lying within k standard deviations of the mean is at least this value. So if you have a mean value and you want to be within so many standard deviations, this will tell you how much percent of the data is there. This does not need a symmetric distribution like the empirical rule does. So Chebyshev's theorem, because it says at least, then it works really, really well for giving an approximation and the minimum value of the data that you would get. And so k in the number of standard deviations goes up in predictable form. So 1 minus 1 over 2 squared is 1 minus a fourth or 3/4. And 75% of the data is within 2 standard deviations. And within 3 standard deviations is 88.9. Now remember, this works with non-symmetrical data. And so here's an actual good example of this, applying Chebyshev's rule. In Georgia and Iowa, we have data that shows the age in years and the population. And so the Georgia population has a mean of 38.2 and a standard deviation of 22.6. But this is not symmetrical within a bell curve. So you want to know how many people are within 2 standard deviations of the mean, again, the mean being 38, then you would use Chebyshev's rule. And Chebyshev's rule says that this would be that 75% would be within 2. Right, if we go back to the previous screen, 1 minus 1 over 2 squared equals 3/4 or 75%. So we're looking for 75%. And so what we need to kind of find is the boundary of 2 standard deviations. And so the boundary of 2 standard deviations is the mean minus 2 times sigma, which would be -7, which doesn't exist, right? We don't have -7 years. And then the mean plus 2 sigma, or 38.2 plus 2 times 22.6, and that's 83.4. And so you can say at least 75% of the population of Georgia is between 0 and 83 years old. So 90 is more than 2 standard deviations out. So we're going to say, oops, I keep shutting that window, that 90 is unusual. And the idea of usual, unusual is an idea of how far things spread out by the standard deviations. The book generally has a 1, 2, 3 rule. Anything within 1 standard deviation is considered to be not unusual. Anything over 2 standard deviations is considered to be unusual, and things past 3 standard deviations are considered to be rare. All right, what we want to do now is we want to look at using the midpoint to calculate standard deviations for group data. And what we can do is we get a similar calculation, but we need to take into account the frequency because we're going to be using the midpoints again. And so our x value won't be the actual data, but it will be the midpoints. And so we're going to use a frequency chart, and we're going to build a column for the deviations of the midpoint squared times the frequency of each midpoint, and then we're going to take the sum of that. So let's look at some group data here. We have the number of children in 50 households. I'm not going to have us break down and do the frequency distribution separately. We will grab it from existing again. We'll grab it from the existing slide. And what we're going to do is we're going to enter this data here. We're going to enter the frequency distribution of the group data and the frequencies. And 2 seconds here. So try to get my Excel ready to take our data. In fact, we're going to do this with the data that we already had that we used as in chapter 1, or not chapter 1, section 1, because we already have the midpoints and the frequencies for our data set here, and this was the cell phone data. So let me bring this back up here. And so here is the midpoints and the frequencies from our class data with the cell phone data. And we're going to look at making, finding the standard deviation for this, since we have already found the mean. So let's look at our formula. We want to take the sum of the deviation squared times the frequency, and then divide it by n-1, and then take the square root. So we're going to turn that formula into a table again. So we'll keep the frequency here. But I'm going to get rid of the x times f. So to keep things nice and neat here, I'm going to copy this and put it onto a new cell, or a new sheet, sorry. And I'll paste it here. Oh, it lets me paste. Did I not hit copy? Copy. Go to my new sheet. There we go. And so this was our data from section 1, where we looked at, did our frequency distribution of the cell phone usage. Now what we want to do is we calculated the mean of that. By taking x over to x times f. Sorry, I keep clicking to move things about, and it shuts the browser window. So this was the created table that we had before. So we have the mean. What we need to do now is we need to calculate our deviation. So this is going to be x minus the mean. I'm going to write u for mu right now. And so our x value is equal to b3 minus our mean, which is in G10. But because it's always going to be in G10, we're going to put dollars around it. G $10. And there we get our deviation. So we'll scroll down and get all of our deviations. I'm going to try to move my mean here. And I'll move it to a better place. And now we're going to square our deviations. So I'm going to take my value for E3, and I'm going to carry it 2. I'm going to square it. And then I'm going to pull down and copy that calculation. Again, if we look at what we want to do, we've taken our deviation and squared it. And now the deviation squared is going to be times the frequency. So this is where we differ from what we did before when we were calculating the standard deviation. So again, I'm just writing columns, headers up here so we know what we did. We're going to multiply it by f. And so in this case, we now have f3 times, well, our frequency is C3. And we'll bring this down. And now we're ready to take our sum. So this is the sum of our deviations times the frequency. And so that is equal to the sum of G3 to G9. If I can type my parentheses correct. And so we get the sum of the G3 to G9. And I'm going to keep jumping back and forth for the formula with us here. So we've summed the deviation squared times the frequency. So we now have this upstairs part. So we need to divide it by n-1, which is our count. Notice how formulas in statistics, because of the sums, they turn into processes of adding things up. And so now I have the sum of my frequencies here. So I need to calculate my standard deviation. Let's calculate our variance first. Our variance, which is the sum of the deviations divided by n-1. And n-1, n was this part here, our 30 things. So I'm going to do an equal sign. Now again, these things are locked in place, so I don't want to change them. So I'm going to do dollar $G11, whoops, dollar $G $11. Remember, our dollars are our anchors, and they for things that are in one place, we use that to anchor them, versus when we have equations where the values are in columns and we drag down. I'm going to divide it by, and I'm going to put parentheses here, because it's going to be our n, which is C10. So $C $10 minus 1. And so there's our variance. And our standard deviation is the square root of the variance. So that's equal to square root J3. And so our standard deviation in the data set of cell phone data we were doing was 62 minutes coming across. So calculating a standard deviation from a data that's coming from a table, we have to do a lot more work. We have to get the x times f, sum that up, calculate the mean. Then we have to calculate the deviation from the mean, square the deviation, and then multiply it by the frequency. We then sum up the frequency times the deviation squared, and we divide it in our formula here by n minus 1. So notice our formulas become construction rules. But we can at least get a standard deviation even if we only have a table of data. All right, now I noticed while I was presenting here that in one of the examples in the slides, they accidentally put double square roots. But notice when they actually do the calculation, they only did the square root once. So for some reason, someone typoed here and there's double square roots. So if you're looking at the examples in the slides, that's just a mistake in the slides. And we use the midpoint of classes, so that works fine. The last thing I want to talk about is the coefficient of variation. What the coefficient of variation does is it makes a percentage, being if we're in a population or a sample, of the standard deviation divided by the mean. It's a ratio of the spread versus the mean value. And that gives a percentage of what the standard deviation is related to the mean value. So this is called a coefficient of variation. We take whatever our standard deviation value is and we divide it by the mean. This is useful for comparing two different things. And what we want to do is let's find the coefficient of variation for both of these. So what we're going to have to do is find the standard deviation and mean for both sets of data. So again, I'm going to set up a new spreadsheet. So we have heights and weights that we need here. So I'm going to make a column for heights and a column for weights. Then we're going to pull the data off that slide. So we have 72, 74, 68, 76, 74 again, 69, 72, 79, 70, 69, 77, and 73. So there we have the heights of the basketball players. And let's get their weights in place. 180, 168. 225. Oops. 225. 201. Sorry, the screen keeps disappearing here. There's one button I go to click, and if I miss it by a little bit, I'm going to try to move some of the buttons around. 189, 192, 197, 162, 174, 171, 185, and 210. Hardest part about statistics is sometimes the data. All right, so what we want to find is we want to find the coefficient of variation for the heights and weights. And so if we come back to our equation here, So there's the heights and weights that I plugged in for the basketball players. But our equation says the coefficient of variation is the standard deviation divided by the mean. So we need to calculate the standard deviation and the mean for both sets of data. And since this is an entire basketball team, we're going to do it as a population. So I'll go the mean of the heights is equal to, we'll use average. And our data starts on B2 and goes to B13. The mean of the weights equal average. And that goes from B2 to B13. Or from C2 to C13. Then we need the standard deviation. So equal sign STDEV dot P of B2 to B13. Whoops. I typed over my standard deviation is the standard deviation dot P. Standard deviation dot P of B2 to B13. Standard deviation of a population, B2 to B13. And I think what I want to do here is say that's the height, so we can, and the standard deviation of the weight is equal to standard deviation dot P, because it's a population, from C2 to C13. And so the coefficient of variation, the CV of the height, is equal to the standard deviation divided by the mean. We're looking at the ratio of the standard deviation divided by the mean. So the standard deviation divided by the mean for the heights would be F3, there's the standard deviation highlighted, divided by F2. And then we multiply by 100 to turn it to a percentage. And so it's 4.52%. The coefficient of variation for the weights is again going to be the standard deviation. So that in this case is H3 divided by H2, which is the mean, times 100. And that has a coefficient of variation of 9.4%. And so the coefficient of variation is standard deviation divided by mean. And if we look at it, in detail, then we can see that the weights are more variable than the height. So we look at the ratios, the weights have a 9.4% change, while the heights have 4.5%. And notice that this gave us the ability to attach a number to two different things and compare how they vary, because by making them a ratio to what we measured, the variation became a percentage. All right, that wraps up chapter 2.4. I am going to, I want to show one thing here. Let me see if I can pull it up in the web browser, because this is important for when you're doing the homework set. So let me get to the browser here. Let's see if I can get the whole web browser shown. Take a second to redraw the screen here. Apologize, I want to show the web browser completely, but I had to blow up to fit in the chart that was on the one page. not letting me redraw this. I'm just going to recreate a new one. Bear with me 1 second here. As I delete this, and I'm going to add the web browser back. And I want to add the web browser back. There we go. There we go. My apologies for trying to resize things to zoom on the image. And what I want to go to is inside of the assignments. And let's see if I can view an assignment here. Preview. I think this might have one. Yes. When you have a homework in Pearson, you'll click to view the data set. And there's a box up here in all of them that if you click on it, you can open in Excel. When I click on that, it opens up a window asking me to save the file. And if you save this file, you can open it up into Excel, and that way you can do your calculations and you don't have to type everything in. If you noticed in doing these videos, one of the longest parts was typing the data sets in. So the homework has this ability for you to open into Excel or even copy to the clipboard. And if I copy to the clipboard, if I did it right, I can paste it into the web browser. So there are different ways you can get the data in where you don't have to type everything in. And then you can go quicker than Professor Thompson did. Email me if you need anything.